Alexander is much more comfortable, but he's younger, so you have that. We'll try to use this. Better?
Yeah.
So I was saying, this is an important occasion because this is the first best SISFA Best Paper Prize 2017 to promote young scholars. It is not a very big prize in money, but it is symbolic of the way we want to go on with our society. And so Alexander Blum will talk his works at the Max Planck Institute for the History of Science in Berlin. And he's the winner of the prize I mentioned. And so he will talk about the kind of researches for which he won the prize. So he will speak on how quantum field theory became a theory of scattering. You have 25 minutes in all, so we leave a few minutes for questions and discussion. Thank you.
Yes, so thank you very much. First, let me apologize for giving this talk in a t-shirt. That was not the plan. I had a nice Italian shirt in my suitcase, but as it turned out, my suitcase is not waterproof. And this was the best outfit I could muster. So that is not in any way meant to show any disrespect. And to the contrary, I'm very, very happy to be receiving this prize. My first prize as a historian of science, and it's a great honor to be the first one to receive this prize from such a unique society devoted specifically to the history of physics, the subject to which I have, over the last few years, devoted my life's work. So it's a great honor, and thank you all very much for having me and for bestowing this honor upon me. It's also a great pleasure for me to get the prize for this specific paper, because it is not only my favorite among the papers I've written so far, it is in a sense also the paper that I went into the history of science to write this paper. So I got my PhD in physics, but realized that there were questions within physics that I felt I could only address from a historical angle, and that was the main driving force for having me move from physics into the history of physics. So the specific question that I wanted to address in this paper, and so it's very unusual also for me to give a talk about a paper that I completed almost 2 years ago now. I tend to, in my talks, always present work in progress and use the talks to give me a deadline to push my papers onwards. So I'm going to be taking a somewhat more reflective angle now in giving this talk. Reflecting on the question I asked and how I attempted to answer this paper. And the question is, I put a 1 here, but it's really actually the only question we have. How did quantum field theory become a theory of scattering? I should say a bit more about this. When we learn introductory quantum mechanics, there's of course a lot about quantum mechanics that is very, very strange and novel, and this has been amply discussed over the last century. But in one sense, quantum mechanics looks very much like the kind of physics that we're used to from Newtonian physics, say. We have some way of describing a state of the world at some time, and we have a differential equation that tells us how this state evolves in time. Of course, the question of what exactly that state is in quantum mechanics and the wave function is the central issue in the interpretation debate that has been with us for almost a century. But still, on the face of it, it looks very much like the kind of physics one was used to in the 19th century. Now, if one compares this with quantum field theory and the way it's taught in introductory courses at universities and in textbooks, that is, on the other hand, a grave departure from the way one normally does physics. No longer does one centrally talk about describing the state of the world and evolving it in time in differential equations. Instead, almost all quantum field theory classes would start with the issue of calculating scattering matrix amplitudes using Feynman diagrams. That is the bread and butter of quantum field theory. And it's really a very, very different, not a differential view of the world where we have at one instant in time the world fully described, possibly accessible to some Laplacian demon. Instead, we just talk about inputs and outputs, black boxing the detailed dynamics of what goes on inside. And my question that I wanted to answer in this paper was, how did this happen? And in my research on that, the first thing that became clear, this is indeed a historical question. For if we look at early quantum field theory, which was developed basically right after the creation of quantum mechanics in the late 1920s by the likes of Paul Dirac, Pascual Jordan, Wolfgang Pauli, and Werner Heisenberg. This early quantum field theory still looked a lot like quantum mechanics. So this equation here is from the first paper on relativistic quantum electrodynamics by Pascual Jordan and Wolfgang Pauli. And it is, just as you would expect from Newtonian physics and quantum mechanics, a differential equation for a state functional psi, which is a functional of the field configuration of the electromagnetic field tensor. And we have a differential equation for that state functional. And as Jordan and Pauli remarked on their paper, these equations they write down are supposed to play an analogous role for an isolated radiation field, as the Schrödinger differential equation plays for a specific quantum state of an isolated mechanical system. So it was by no means a foregone conclusion that quantum field theory would be formulated as a theory of scattering. To the contrary, initially people by default wrote down differential equations that would describe the evolution of a state. And so that gives another impetus to believe the question of why quantum field theory is formulated nowadays as a theory of scattering is a historical question. Now, if we would ask a working physicist why quantum field theory is formulated in this manner, there might be several answers that we could give. And we're going to look at some of those in the course of this talk. And I will try to reflect on how historical analysis can give us an insight into what is actually the most important reason and the driving reason. Because that as soon as you reach the point of thinking about quantum field theory in that way, it might be hard to reconstruct why you're actually doing it that way. And so the historical analysis becomes important. Because one obvious reason one might feel for why quantum field theory is formulated in this manner is that quantum field theory is often and rightly described as what we get when we merge quantum mechanics and the special theory of relativity. And the special theory of relativity, of course, as we all know, puts space and time on an equal footing, and thereby makes it somewhat problematic to focus exclusively on evolution in time, to single out time. And so there is, in thinking of space and time together, a certain element of relativity that, rather than looking at the state of the world at one specific point in time and then working with that, to rather look at overall processes. And indeed, in attempts by Paul Dirac to implement relativity into quantum mechanics, this was really Paul Dirac's central focus of his research all through the late 1920s and 30s, there is visible a certain transition from wave functions that describe the state of the world over to something more procedural, describing transition amplitudes. And this was one of the starting points also for Richard Feynman in his development of his formulation of quantum field theory. However, if we look at the actual history, how this plays out, there are several reasons for thinking that relativity is not the central reason for quantum field theory being described in that way. On the one hand, while relativity brings us to look more at processes rather than the state at a certain instant, it does not explain this focus on scattering, which is not just looking at some kind of process, but rather looking at a very specific kind of process where we just know what comes in the infinite past and just know what comes out in the infinite future. And actually, if we look at also the development of quantum field theory after World War II, which is the time when the modern quantum field theory is developed by the likes of Julian Schwinger, Shinichiro Tomonaga, and Richard Feynman, we actually have formulations of quantum field theory that are fully implementing the special theory of relativity, but still look absolutely like the kind of differential equation physics we're used to. Here is in Schwinger's hands, these are his notes from the Oldstone Conference in 1948, a differential equation for the state function, just like we saw it before. The only concession that's made to relativity is that it's no longer a sharp instant in time, but rather a space-like hypersurface sigma. And Tomonaga, who also derived this equation, which is known as the Schwinger-Tomonaga equation, portrayed this equation as a generalization of the Schrödinger equation. So looking at the historical development, we can say, while relativity may have played some role, it is certainly not as if the mere implementation of special relativity into quantum theory is what forces you to think of quantum field theory as a theory of scattering. So a second reason you might think of is experiment. Scattering experiments is just what we do nowadays, and so that's why it became the way we should be thinking about quantum field theory. People used to do spectroscopy looking at the stationary states of atoms. Nowadays they do collider experiments and collisions. And so, of course, we should formulate our theory in terms of scattering. And there is a certain element of truth to that. If we, for example, look at Heisenberg's work on the S-matrix. So I'm mentioning lots of things here. I opted not to go, also because of the short amount of time I have, for like a big narrative, but rather on a reflective point of view. So if any of the names and features of the theory I mentioned, if you want to discuss them later on, I'd be very happy to. So there's Heisenberg's work on the S-matrix, which is the scattering matrix, so that is a foundational part of the formulation of modern quantum field theory. Indeed, when Heisenberg formulated this S-matrix approach to quantum field theory in the 1940s, he was partially motivated by the new kinds of experiments that no longer dealt with stationary states of atoms or molecules, but rather dealt with collision events. Not in colliders yet, those had not been built, but in cosmic ray events, which are of course similar, that you have some high energy particle coming in from infinity, and then you measure what comes in, basically comes out at the surface of the Earth. So again, there's a certain element of a shift from experiments looking at stationary states to experiments looking at scattering, but again, it's hard to see why this would have been the central reason, for several reasons. On the one hand, we see that while we did have some scattering experiments in cosmic rays already in the 1930s, when we look at scattering as the dominant way of doing physics, that is in particle physics nowadays, where particle physics is basically synonymous with looking at collision and scattering events in particle accelerators. That really only became the dominant way of doing particle physics after quantum field theory had been established as a theory of scattering. Only beginning in the late 40s, at a time when this novel formulation of quantum field theory as a theory of scattering, which happens also around that time in the late 40s, mid to late 40s. Only after, and we might actually turn this around and say one of the reasons why people tended to think of particle physics as accelerator physics, as collision, as scattering physics, was because the theory was formulated that way. That was the simplest problem you could tackle with a theory, and so you would build machines that would look at scattering events. And the actual key experiments that drove the development of quantum field theory in the 1940s were not these kinds of scattering experiments at all. The key experiments in the 1940s were precision spectroscopy experiments that looked very much like the kind of experiments that had originally led to the formulation of quantum mechanics as a theory of stationary states evolving in time. These are, for example, the Lamb shift, which is just basically a much more precise look at the hydrogen spectrum, which had originally given rise to quantum mechanics. So by looking at the history, it turned out that the central reason for why quantum field theory in the 1940s was reformulated as a theory of scattering, rather than as a theory of instantaneous local quantum states evolving in time, was the need to deal with infinities. As you may know, all through the 1920s and 1930s, quantum field theory was beset by great difficulties. You could, in the first approximation, do some good calculations with it, but as soon as you went to higher approximations, you would always get infinite results. And the theory seemed to be fatally flawed. And in view of this, many physicists, including Heisenberg and Feynman, thought that the problem with these infinities was precisely that you were trying to look at the whole thing in too much detail. You were trying to describe a state in quantum field theory, as it did in quantum mechanics, as a state at a specific instant in time and uniquely determined at each point in space and time. And so they believed that one was overreaching in trying to formulate quantum field theory in that way, and that all quantum field theory could ever be was a theory, a black box basically, where you look at just what comes in and what goes out. Now, it turned out in the late 1940s that this was probably an overstatement. You could, at least in principle, we've seen that with the Schwinger-Tomonaga equation, write down a formulation of quantum field theory that looked just like quantum mechanics and was a differential equation describing the evolution of a state. However, you needed to use certain techniques to remove the infinities that appeared. And these techniques are, to this day, known as renormalization methods. And while it was felt that getting rid of differential equations entirely had been throwing the baby out with the bathwater, it was the case that renormalization, the method to get rid of the infinities, was in fact best implemented within the scattering framework, within a framework using an S matrix. And so, as this process for removing infinities, this renormalization methods, became a central element of quantum field theory, it also became clear that since these methods were best implemented in a scattering framework, that would be the foundational way to describe quantum field theory, and also the way in which you would be presenting it to students learning the subject. Now, of course, one might always argue that this might be a historical coincidence. It just happened so that there were some physicists who were thinking in terms of scattering. Those physicists developed renormalization methods, and so the renormalization methods developed within that framework. And the historical argument really just shows you that the whole thing is kind of path-dependent, and one might, if one goes back to first principles, reformulate quantum field theory just as well in the usual manner, using differential equations. And to see whether that is really the case, one would have to talk about other possible worlds in which quantum field theory might have been developed differently, and we get into very difficult issues of counterfactual history. But in the history of quantum field theory, we have the great advantage of actually having a parallel world happening. And that is in the work of this man, Ernst Karl Gerlach Schütterle. He is famous nowadays for having invented lots of, found lots of results that were later discovered by other people. He was working in Geneva in relative isolation. He published all of his papers, or basically all of his papers, in French, supposedly, even though he spoke German as a native language, supposedly because he always dictated his papers, and his secretary only spoke French, so he would dictate his papers in French. And also, even aside from the fact that the papers are not written in the standard languages of physics at the time, They are also incredibly hard to read. They are, one must say, that poorly written with very confusing notation. And so they really, in Stuttgart's own little Geneva agenda, they represent a sort of parallel world where he developed renormalized quantum field theory independently of Feynman, Schwinger, and Monade, taking a very different starting point, his so-called causal perturbation theory, which is an iterative construction of the S matrix, rather than a semi-derivation of the S matrix from a differential equation, from the Schwinger-Monade equation. And so even though we started from a very different starting point, and had very different aspirations also, reformulating mechanics in this manner, we see again exactly the same thing happening. Again, he develops a method for removing the infinities in quantum field theory that had been plaguing quantum field theory for 20 years. And again, even though developed absolutely independently, again this modification, these renormalization methods, are only possible to be implemented within the S matrix frame. So the history, by having this alternative world, this alternative story for the development of renormalization methods, he developed these about at the same time as Feynman and Schwinger did, and he came a bit too late. But by having this alternative history to look at, we see that there appears to be a certain amount of necessity that removing the infinities from quantum field theory really almost unavoidably was what drove people into moving away from differential equations and actually reformulating the theory in terms of scattering as a black box where you have in-states coming in and out-states going out. And just as a small outlook, we are currently looking at in more detail also at the further development of Stuttgart's work, because he continued all through the 1950s to discover things that people only discovered later on. It's very hard work reading these papers, which are very hard to read and very inaccessible. But there are also, for other cases, such as the development of the renormalization group and looking in detail at Stuttgart's causal perturbation theory, he continues to provide a very good backdrop to consider alternative ways the theory may have developed. So let me conclude. So as I pointed out in the beginning, if we want to look at the question why quantum field theory is nowadays generically represented as a theory of scattering, we first realize that this was not always the case. That early quantum field theory was structured on quantum mechanics, had a Schrödinger equation, looked at stationary states, and had the energy values of these stationary states at its center. And we realize historically, by looking at various different ways in which the theory developed, that this focus on scattering amplitudes moved to the fore specifically because they provided the right locus for implementing methods to remove the infinities, to remove the divergences. And that gives us an insight into physical theory that a mere reflection at the current status of the theory could never provide, because there, as I showed, you might assume several different reasons. And it's very hard to see once the theory is finished which one of those was actually the one that molded the theory into the form it has today. And so I was very happy to provide a historical argument that, to my view, gave the best possible answer we can give to the question, why is quantum field theory, even though it's supposedly just a quantum theory like quantum mechanics, look so different? Why it is a theory of scattering, and why the state vector, the Schrödinger wave function of quantum mechanics, doesn't entirely disappear, it's not abolished, it's there in the background, but why it withers away as scattering comes to the fore and becomes the paradigmatic problem to be calculated in quantum field theory. Thank you very much.